Previously we learned how we can assign new values to our rows and columns. And we did so by first indexing the data frame with either log or ilog, to which we pass either the explicit or the implicit index. The explicit index could be, for example, the name that we give to our column, and the implicit index simply refers to 0, 1, 2, 3, so it's the same as we would index a list or a numpy array. And we can also use directly just the square brackets and then pass, for example, the column name, but usually as our indexing gets more complex, this is not preferred because we might confuse the explicit and implicit indices. Here we have a simple toy data frame with one column that has the numbers 0 to 4. And so now if we want to modify this data frame by, for example, adding a new column, and the explicit index here is b, which will be a new column, so this column does not exist yet, and to that we assign the string hi. And now you might say, don't we need 5 values for the data frame because we also have 5 rows in here? But Pandas does something that's called broadcasting, which makes sure that the shapes are matching. So if we run that, then now we have a hi in all of our rows. Now, when we're adding values, we can also do that based on our old values. So in here we add another column C, and C should be 4 times the column A. So we run that, and we get 4 times 1, 4 times 2, and so on. Now in this video we will look at some more elaborate ways of modifying our series and data frames. When you search online how to modify values in series or data frames, you will probably run across the functions apply, map, and apply map. And these functions are very convenient because they allow us to apply any function to the elements of our series or data frame. The big problem is that these functions will be applied element-wise, and thus we're not making use of vectorization. If you think back to the math with NumPy video, you might remember that vectorization means that we're doing our computations not element by element using Python's slow looping, but instead the computation is offloaded to C, where it can be run on multiple elements at once. So while these functions are very convenient, they're not efficient if we compare them to vectorized code. That being said, we will still cover them in here because they can come in handy if our function is too hard to vectorize or we just don't really care about speed that much. Here we have a nice overview that shows us the difference between these functions. And we can say the main difference is that map works for series, apply map works for data frames, and apply works for both. Okay, let's check out apply. Here we have again our toy dataset, and now we want to apply some function to it. And so we call on the data frame the .apply, and then to that we pass our function, which here is np.sum. Very important, we're not writing the brackets here, which would indicate a function call, but we're just passing the function. Besides that, we're also passing an access argument, which specifies in which direction the function should be executed. So axis 0, the default, tells apply to perform the function column-wise, and axis 1 would refer to row-wise. So before running it, we can imagine first the column A is summed up, then column B, and then column C. Let's confirm that. And indeed, this here gives us 10, C gives us 4 times of that, and in B we have all the highs. Now let's say we want to apply the sum function, not column, but row-wise. So we want to sum 0, high and 0, 1, high and 4, and so on. And if we try running that, we get a type error. And that makes sense because we cannot add integers and strings together. But that's no problem for us because we can define a custom function that also turns the integers into strings. So here we define our function, and this function gets an x. And depending on what we pass to the access argument here, the x will either represent the individual rows or the individual columns. So we think back, the axis 1 was row-wise, so then in this function here, we define what should happen to the individual rows. And so what does happen is that we have a formatted string here that takes the first, second, and third element of our row and turns everything into a string. Let's run the apply, and we can see that we successfully combined all the columns. Now, if we want to save this result, we can assign it to a new column. So we write df, our square brackets, put the new column name in here, and then just copy paste our apply in here, and we have a new column. When our functions are as simple as this here, so it's just one line, then it can also make sense to combine the apply with lambda functions. And for that, the syntax is exactly the same. So we have df.apply, we have an access, but now instead of passing the function, we pass a lambda function. So our lambda function also looks at the individual rows and then does the same thing as we defined in here. And if we run that, we get the same exact output. Okay, now on to Applymap. And we said that this function doesn't work for series, but on the whole data frame. What we want to do in here is duplicate all of the elements. So out of the 0, we want to make 0, 0, high should be high, high, and this for all the elements. And so for this to work also on the integers, we first cast everything to a string by passing the string constructor to the Applymap. And then the second Applymap will look at all the elements and multiply them with 2. And now since everything's a string, we're not multiplying any numbers, but duplicating the strings. So we run that, and now everything is double. Next up we have map and also replace. Both of them can be used to substitute values of a series. So we have a data frame here and we take the first column, which gives us this series here. And what we want to do is we want to replace the integers with strings. So the integer 0 should be the word 0, 1 should be 1, 2 should be 2. And if we run that, we can see that for the values where there is no existing mapping, we have nans. So we defined the mappings in here as a dictionary with key and value. The key is the original value and the value is the new value. And if there's no key value pair for any of the elements in here, then they will be mapped to nan. In case we don't want to map all of the values, but just replace specific ones, we can use the function replace. So this will also replace the 0, 1, 2, but since we didn't define anything for the 3 and 4, they are left in place. Okay, so much for the apply map, and map, which are very convenient and easy to use, but also very slow, because all the functions are applied element by element. And also because type checking and broadcasting has to be done in the background, they usually have a bigger overhead. So everything takes a little longer. So how can we get rid of loops and this overhead? And the solution to that is vectorization. And while there is a function that is called np.vectorize, usually it's not as easy as that to turn our function into a vectorized function. The basic idea behind vectorizing our functions is not using explicit loops and using functions that are vectorized. And these functions usually come from NumPy, but also Pandas or SciPy. So with these functions then we can build up to the same functionality of our original function, which is often possible, and if not, then we can still rely on apply. So now you're probably thinking, how much faster is vectorization? And so we will look at some examples of how we turn non-vectorized code into vectorized code, and also compare how much time we save. And we start off with an example for numeric data. Here we have a data frame with 2 columns, A and B, and both of these columns have 1 million random floats that are between 0 and 1. And what we want to do is simply add these 2 columns together. And the slow, non-vectorized way of doing it is using apply. So we apply to our data frame the lambda function that checks every row and sums up the value of column A with the value of column B. Let's run that, and we can see on average it took 4.68 seconds to run, which we can check with the cell magic time it. So let's compare it to the vectorized version. And in here we're simply adding up the 2 columns, which then internally uses the addition defined for Pandas series, which is vectorized. Now running this took just 613 microseconds, which is around 7,000 times faster. And we can even go further. If we write after a series the dot values, then returning our series into NumPy arrays, which then removes the Pandas series overhead that this calculation here has. So we run that, and we're getting not much, but still a little bit faster. Okay, now this was a very simple example. What if we have more complex functions that, for example, make use of conditionals? So in here we have a data frame that has in one column regions, we have EU and USA, and then we have measurements of temperature, first in Celsius and then in Fahrenheit. And the function we want to apply to this data frame should select the temperature unit in accordance to the region. So for EU it should select Celsius, and for USA Fahrenheit. And we can see that in here. So if the region is EU, we return Celsius, otherwise we return Fahrenheit. And if we apply this function row by row, it takes us more than 400 milliseconds. The vectorized version of this makes use of np.where. And np.where first gets a condition, which in here checks if the region is equal to EU. And in the rows of our data frame where this condition is true, it will take this value from the same respective row. So if the region is EU, we take the Celsius value, and now if the condition is not met, then we take Fahrenheit. and because np.where is a vectorized function, we can run it and we'll see a significant boost in efficiency. And indeed, we're about 100 times faster. Okay, but what if we have more than one condition? Because normally our function might also include an elif. So here we have a data frame that has 100,000 values that are between 0 and 4 because the high is exclusive. And what we want to do is map these integers to colors. So each of the values should respond to a different color. 0 should be red, 1 green, 2 blue, 3 yellow, and 4 purple. And without vectorization, just using our apply, this takes 600 milliseconds. To now vectorize this, we make use of np.select. And to np.select, we can pass conditions and choices. And so the conditions are whether the value matches to 0, 1, 2, 3, and 4. And depending on the conditions, we take the choices either red, green, blue, yellow, or purple. And again, because np.select is vectorized, this will only take 2.45 milliseconds. And of course, for this example, we could have also used the map function, but the np.select gives us in general more flexibility, because we can base our conditions not just on one column, but on any column. And also in the choices, we can put values of the different columns. Let's go to one final example, which is for logical operators. Here we have a data frame with 2 columns, each with 100,000 values. And the values are either 0 or 1. And what we want to apply is the logical AND. So we run here the d of .apply with a lambda function that checks each of the rows and checks if the value in column A and in column B is true or 1. We run that and it takes 400 milliseconds. Now again the same but vectorized. And this time we use NumPy's vectorized function logical AND, to which we pass both of the columns, we run that, and now our computation takes about 2000 times less time. We can speed that up even more by again adding the dot values, which removes the Pandas series overhead, and now we're down to 60 microseconds. I hope these efficiency boosts motivate you enough to not always rely on apply, but of course also vectorizing can be hard, and if you want some more additional resources, you can check out these links here.